Okay, welcome to another video on empirical asset pricing. Now, this video is concerned with providing an alternative to the J statistic, which we've discussed in the lecture, and that was also discussed in those previous videos where we actually derived that the distribution of the J statistic is the chi-square distributed random variable with degrees of freedom equal to the number of moment conditions, in our context test assets, minus k, which is a number of parameters. So take a look at the previous videos for the derivation of this result. Now, the alternative to the J statistic can be used when you use what we call efficient weighting or efficient GMM. And that entails using in the generic GMM formulation an AT matrix, which makes sure that it converges to this term d prime s to the minus 1, and the term that we see here is such an efficient weighting that it can actually produce such a convergence. Okay, we had this in the lecture. Now, if you choose to perform such a GMM estimation, use this weighting, then you may also resort to another form of the J statistic, an alternative to it, which also happens to be chi-square distributed with the same degrees of freedom, but with a derivation that differs from the quadratic form that we see up there. Okay. Now, to see this alternative form, what we need to do is essentially perform a task that was asked to perform in a question for review. So in the lecture, remember what we did is we derived the limit distribution of the sampling error blown up by square root of t, and we exploited the mean value theorem for that purpose. And one of the questions for review was asking you to actually plug in the result back into the mean value theorem expression for gt of b hat, which we see here again. Okay, and what we should use then when we plug it back is we should use the efficient weighting scheme, right? So if you would go for objective-based GMM, that's the weighting matrix that you will use for that purpose. Okay, so the idea is take a look at the results that we have for with respect to the limit distribution of the sampling error, and how this form looked like, and how we can plug this thing back into the mean value theorem representation. So if you have not done it yet, you should actually perform this question for review to see what is done in the next step. Because in the next step, I'm doing precisely that. I'm plugging back the results into the MVT expression. Okay. So I'm doing that, and I get GT of B hat. And now comes the plugging back result. I get an expression that reads as follows. Which is multiplied with square root of t gt of b. Okay. Now this is what you should get if you correctly plug in the results from the lecture into the mean value theorem expansion, and when you would use the efficient weighting matrix to do that. Okay, to verify that you have that result. Now, we take a look at this expression. We note the following things, or we should recall the following things. Well, with this term, we have assumed that we could apply a central limit theorem, which is justified from estimate pricing theory, which states that the series of pricing errors follows a martingale difference sequence, and the martingale difference sequence allows the application of a CLT, so we can justify that this underbrace term converges the distribution to a random variable, let's call it x, which is distributed normally with mean 0 and a variance covariance matrix, which we refer to as S. Now let me also denote the term that we have here for convenience with M, maybe with a hat over it. And we could look at, what we should look at this point, I think it's helpful to do so, at the rank of the matrix of that matrix which we have in these brackets here. Okay, what's the rank of this matrix? The result and the answer to this question would be to look at the following thing, right? Here we have a vector of normal variates, and there are no linear dependencies in these normal variates and these n sample means. Okay, and over there we have GT of B hat. We hopefully recall that per construction of GMM there are linear dependencies built in this GT of B hat vector. As a matter of fact, I can represent k rows of GT of B hat as a linear combination of the n minus k remaining rows per construction of GMM. So what I'm going to do is I have something of a random vector, this guy here, which has n linearly independent random variables, and I multiply it with a matrix, n by n matrix, and I produce linear dependencies in GT of B hat. It must be the case that the matrix in brackets that we have here, it cannot be of full rank if I produce k linear dependencies in GT of B hat. The conclusion is that this matrix in the green brackets is actually of rank n minus k. Okay, we should note that here. The rank of that determined brackets is n minus k. It's an n by n matrix. The whole term in brackets is an n by n matrix, but its rank is n minus k, as GT of B has n linearly independent vectors, or n linearly independent random variables. Okay, but GT of B hat, that's a random vector which has k linearly dependent random variables. Okay, they can be represented as linear combinations of the n minus k others, and that entails that the matrix in brackets must be of rank n minus k. And we keep that in mind because the rank of that matrix is going to be important later. And I would perform a little manipulation of that expression that we have here. And by the way, I just realized that I've forgotten to pre-multiply square root of t on this side, so I have multiplied square root of t on both sides of the equation, and we should of course have it in both sides. Okay, so we're going to manipulate this equation in another way, and maybe we'll write it here. Okay, then note what I'm going to do here is I'm going to make use of the fact that the symmetric matrix S hat, that's my estimate of the S matrix, can be written using a matrix C hat, which is multiplied with C hat prime. That's sort of the idea that we got from a spectral decomposition, but essentially what we're going to do is we're also going to shove the eigenvalues of that matrix also in the two matrices. So the spectral decomposition would have C lambda C prime, and I can also use such a representation. Okay. Now, so S hat can be decomposed into C hat prime, and what I can also do is I can take a look at the inverse of that estimate and can represent it as a function of these C hats. Now it turns out that the inverse of the right hand side can be written like this. So we have C prime hat here. We take the inverse of it, and we have the inverse of C hat. That is because we can use a result from matrix algebra which reads as follows. You have the product of two matrices, and you're interested in the inverse of these two matrices. And suppose that both matrices are square. What you get is the result that you can write this inverse also as follows. You have the inverse of B, which is multiplied with the inverse of A. And that is actually a result that you can find in green. Let me look it up. That's Green's result. A64, okay, which is pretty useful for our purposes. Okay, I think we already had it earlier. And now we're going to use precisely that result to write the S hat matrix in this form using the inverses. And now what I'm going to do is, using that result, I'm multiplying both sides of the equation by this T hat, C hat to the minus 1. Okay, by precisely this C hat which I got from the decomposition of the S hat matrix. Now what I get is the following. I get square root of T. Here comes C hat to the minus 1 GT of B hat. That's the right hand side. And I'm going to write the left hand side. And on the right hand side, I'm going to write it like this. Okay, so this is what I did on the right hand side. I have to pre-multiply the objects with the matrix, and that does the job. One thing to note is this operation didn't actually change the rank of that matrix. The rank is still n minus k. Nothing has changed with respect to the rank of the matrix. So it's not reduced. It can of course never be increased by such an operation. We can manipulate the right-hand side of this equation a bit. Okay, and we can make it look like that as an identity matrix. So I decided to sort of write S hat to the minus 1 using that decomposition that we see on the right hand side of the slide. And I'm doing that because I wanted to have a matrix which has certain properties, and one of the properties is that well, this matrix here, this one, that's, by the way, the rank of this matrix is still n minus k. Didn't change that, the rank in any case. But what you can show is, you can show that this is an idempotent matrix. You take this matrix and you multiply it with itself, and you get the matrix again. So I like to call this matrix, in brackets, I like to call this matrix A sub t, indicating that it depends on the sample size. And as a matter of fact, this matrix is idempotent. You multiply it with itself, and you get the matrix out of it. Okay, this is something that I leave you to check. Check it out. So what you need to do is actually insert in the object the expression for m, which we have here, right, to see that the matrix actually is an idempotent matrix. So try, work it out, multiply the write out the matrix extensively, multiply with itself, see that terms cancel out, and that after some manipulation you're ending up with the original matrix again. Okay, so check that out and verify that this is true. Now, take a look at the second term of this expression, this one. Now we already know that square root of t gt of b is going to converge to a normal distribution with mean zero and covariance matrix S. We had that, and now the claim is that if I take a look at this term, okay, that my claim is that this is actually going to converge in distribution to a random variable, call it, let's a random vector z, which is distributed normal with mean zero, but with identity matrix. Okay, so we're converging to a vector of standard normally and independent, standard normally distributed random variables. Okay, so this result requires a bit of an explanation. I provide the explanation of that in a minute, but let us also assume here that this AT matrix converges in probability to a matrix A, and this matrix A is still idempotent. Okay. A sub t is idempotent, and there's no reason that anything changes in the limit. The matrix remains an idempotent matrix. Now, I'll come back to this result here, the star result. I need you to show you that Z is actually standard normally distributed, that this underbraced term here actually converges the distribution to a standard normal, and I shall do that in a minute. The point here is, before I'm going to do that, the point to note is that the whole expression on the right hand side is going to converge then in distribution to the distribution of A times Z. Okay, so something that is standard normal is multiplied with a non-random matrix A, and that happens because of the Slutsky theorem that we've discussed earlier in class. No? Now, maybe as a bigger overview, we've shown that the right-hand side, and thus also the left-hand side of the equation, is going to converge to a linear combination of standard normal variates. Okay. Now, what I want you to show you is the convergence of the second term to a standard normal distribution. So let me let me show you that this actually is true. So I have the star relationship here. This one is this one. And let me show that actually the claim is true. Okay. This happens because of the following considerations. Now remember, square root of t gt evaluated at b is going to converge in distribution to a normal, right? We invoke the central limit theorem. What we can do with this symmetric and positive matrix S, we can decompose it in CC prime as we've done previously, and what we also can sort of use is that C hat to the minus 1, the object that we had previously, is converging in probability to the inverse of C. Okay, so these are the two results that we need. As a conclusion, what we can think of is that we have this term C hat, which the inverse of C hat, which is multiplied with square root of t gt evaluated at b, is going to converge then in distribution to the distribution of c to the minus 1 and call it x. Okay, so x is where, maybe I'll squeeze it in there, x is this random variable which is distributed normal with mean 0 and variance covariance matrix S. Okay, so this is again the application of the Slutsky theorem. Sort of again, and to figure out what the distribution is. So this is going to be distributed like what? It's a linear combination of standard normal variates. So the distribution is going to be the normal. The mean is not changed. Okay, and the variance covariance matrix is then, well, c to the minus 1. Now comes the variance covariance matrix of x. That would be C. So I write it as C prime. So that's S. And I have to take the inverse of C to the minus 1. And that could be written like this. Instead of C prime to the minus 1. Okay. And we should note, in order to write it like that, can write that C prime to the minus 1 is the same as C to the minus 1 prime. That's again a result that we can take from Green, and that would be his result A62, useful result regarding the inverses of matrices. Now, what we're going to see here is that terms cancel out. So C to the minus 1 with C, and here is the inverse of C prime, so the thing also cancels out, and what we get and left over with is the normal distribution with mean 0 and identity variance covariance matrix, which is what we have claimed. Okay. Okay, this was an intermediate result that's going to show you what's going on with this term that we have here. Okay, it is actually something that converges in distribution to a standard normal distribution. Okay. Next step is we can do the following with our equation that we were left with. What I'm going to do is I'm going to take I'm going to transpose both sides of the vectors on the left and the right hand side of the expression and multiply them with itself. Okay, so that's what we're going to do. Let's maybe start with the right hand side. Okay, so this term, transpose it and multiply it then with the untransposed version. That's the next step. Maybe you're going to write it down. What I'm going to do. Okay, so left and right hand side. Right hand side are transposed and multiplied with itself. Okay. So do that with the term square root of t c hat to the minus 1 gt at b hat as the square root of t gt of b hat, and I said I transpose this thing. C hat to the minus 1 then sort of changes its place, and then go and transpose it. Recall the old result, a times b transpose is b prime a prime. Just apply this result to the left hand side. And I said then I'll take the original left hand side, here we go, and multiply it. So it goes with gt of b hat. Okay. Now let's take a look at this thing that we have on the left hand side. And we say, hey, that's essentially a quadratic form. By the way, I forgot the square root of t here, and I'm plugging it in here. So what the left hand side actually is a quadratic form, recognizing that this term is actually s hat to the minus 1. Again, noting that a prime to the minus 1 is a to the minus 1 prime, the result that we already had. Okay, though this term is s hat to the minus 1. So what we get on the left hand side after this operation actually is the value of the GMM objective function if efficient weighting is used multiplied by t. Okay, and that is precisely the random variable that we're going to take a look at to construct this alternative J statistic. Right, this is the objective function of GMM using s hat to the minus 1 for weighting, for WT. And what I did is actually multiply this objective function by t. Now we're actually able to figure out what the distribution of that quadratic form of the objective function of GMM evaluated at the estimates is. What is the distribution of that thing? Now it turns out that the distribution of that term, or the limit distribution, is actually a chi-square, and the rank is open. So let me leave the rank open for the degrees of freedom. Excuse me. The degrees of this chi-square distributed random variable is I'm going to provide this a bit later. Now, why is this thing chi-square distributed in the first place? Now, for that purpose, it's helpful to go back and consider the right-hand side of the equation that we manipulated its left-hand side and to produce this quadratic form. So I'm also going to take a look at here we are at the right-hand side, this thing here, and see what we get on the right-hand side. So I'm using this abbreviated version and saying, okay, I need to transpose the right-hand side, and that means I have this matrix xt. Actually, did I actually define xt? I guess I did not. So let me define xt. What xt actually is this guy here. Okay, that's xt, and xt is multiplied with at. So the right-hand side of the expression actually reads at times xt. Okay, so if we would squeeze in maybe somewhere here, the expression on the right-hand side of the expression, we would get at times xt. And this thing now is transposed and multiplied with itself. Okay, that's what I'm doing here. So I get the transpose of xt, which is multiplied with at. Transpose it and multiply it with at, and multiply this with xt. Okay, so I manipulate the right hand side exactly in the same way as the left hand side. Okay, now take a look at this AT matrix. We said that AT is an idempotent matrix, and that's my AT here. Oops. That's AT. So, well, any idempotent matrix actually is a symmetric matrix, must be a symmetric matrix. And you see, looking at it, then actually it is a symmetric matrix, A sub t. So, noticing that, I can write the expression also like that. It's AT times xt. But we also recognize that that AT is an idempotent matrix, or you should check that it's an idempotent matrix. So I can write the right-hand side as xt, A sub t, xt, and I get a quadratic form, right? Now what we get is we have this convergence, maybe write it here, of xt to a this matrix, call it X, which is distributed normal with mean 0 and identity matrix, right? And AT was converging in probability to this matrix A. Now note that A sub t, that's a matrix which has the rank n minus k, right? We tracked basically the rank of A sub t all the time, right? So this is why I started with basically verifying that the rank of the matrix A sub t is always is n minus k. So starting from here, going down here, and this then gives us the AT matrix down here, and it still is the rank is still n minus k. Okay, so A sub t has rank n minus k, and this entails that this matrix A has also the rank n minus k. Never changes its rank. Okay, now we're almost there. What we have here, we have a quadratic form x sub t at, here's a prime xt, which converges in distribution to the distribution of x x prime a x. Okay, and as a matter of fact, from the earlier videos that we saw, we actually know what the distribution of such a quadratic form is. X is a vector of standard normally distributed an independent normal variance x, and A is an idempotent matrix. And from result 2A in the script and also in the proof in the video, I know what the distribution of that thing is. That's a chi-square, and the degrees of freedom is equal to the rank of the matrix A. Right? C results 2A in the script and the associated video. This is precisely what we've discussed here. Okay. So now this is already the result. So we can show that the right hand side of the equation, this guy, is going to converge the distribution to a chi-square distributed random variable, and of course, so is going to be the left hand side of the equation, our objective function of GMM evaluated at the true parameter values, and the rank and the degrees of freedom of the chi-square distributed random variable is equal to the rank of A, and we figured out, and we know that the rank of A actually is n minus k. So I can write this result here as well. And that essentially is our key result that we need to store away. And maybe write it again. So we have this possibility to write the objective function of GMM, which uses uses efficient weighting. Okay, and this is the thing that you basically get routinely out of the as an output of your GMM estimation. You blow the thing up by t, scale it by t, and the result states that this objective function multiplied by t converges to a convergence distribution to a chi-square distributed random variable, which has degrees of freedom equal to n minus k, and that is your alternative test statistic that you can use to test your moment conditions. You have the original J statistic that you can use all the time. Okay. Now this formulation that we started with is something that you can use all the time, and you get a chi-square distributed test statistic under the null hypothesis that your moment conditions are true. This version of the test statistic that we have here is only usable. You must use it only if you actually use an efficient weighting scheme. Okay, so I'm writing it down again. It's applicable only, this alternative test statistic is applicable only if you use efficient weighting. That is, if your weighting matrix for objective-based GMM is equal to the estimate of the inverse of the variance covariance matrix S. Okay, and that's what I wanted to show here. The point is that this proof is extremely brief in Hansen's original paper, and it's also not very nicely conducted in Cochrane's book or in other econometrics textbooks like Hayashi. So I try to be kind of complete here. As I also noted in the lecture, there is a confusion in the statistical software literature in the sense that statistical software like SAS and eViews and Stata are regularly producing as a result this version of the test statistic, but you should note that if you use a different weighting than the optimal or efficient weighting scheme, you cannot resort to using that test statistic for the purpose of specification testing, for testing your model, your moment conditions. If you use the identity matrix, for instance, you should use the original version of the J statistic that we see here and resort to it. Okay, statistical software developers are aware of the fact. In the manuals, they mention this fact, but as a matter of fact, it's not implemented thoroughly in their programs. They don't for some reason not produce the original version of the J statistic, but produce this one, maybe arguing that anyone is going to use efficient weighting anyway. But that may not be the case. There may be good reasons not to use efficient weighting, especially in the empirical asset pricing class. Okay, so that's what I want to say about this alternative version of the J statistic. Thank you very much for listening, and stay tuned. There's going to come another video on the proof of the efficiency of the weighting scheme for GMM that is going to provide it in another video. Thank you very much, and as usual, see you in class.